Okay, hi everyone. So let's talk about the orthogonal complement. The way you say this is u perp, like perpendicular, which means 90 degrees, which means orthogonal. And so here, capital U is a subset. Usually it'll be a subspace, but you can do this for any subset of vectors in some vector space V. And what's u perp? Well, u perp is just the set of all vectors that are orthogonal to everything in U. Okay, so the set of all vectors orthogonal to everything in U. It's just the set of all the little v's in V such that they're orthogonal to everything in U. Okay, so then that means for all the elements of U, we should have v dot U equals 0. That's another way to say it. So maybe we'll prove some of these examples in class, but for now I'm just going to tell you the answer so you get an intuitive sense of this. So if our set U is the span of 2, 1, in a little two-dimensional space to get our training wheels going. So this is U. Then what's U perp? Well, it turns out U perp looks like this. Okay, and one way you could say it is it's the span of the vector -1, 2. Okay, and another way you can say it is it's the set of all the xy's such that 2x plus y equals 0. Because this is the equation of how you're orthogonal to the vector 2, 1 if you're a little vector xy. And now let's look at if this is your set U. So now you're in 3 space and you satisfy this equation. So what are all the vectors in this space look like? Well, this capital U looks like a plane through the origin. Okay. And if you remember from calculus, we had the equation of a plane is n dot x equals n dot p, where p is some point on the plane. N is a normal vector that's 90 degrees to the plane. So in this case, n would be the vector 1, minus 1, minus 1, which you can see showing up as the coefficients in this equation when we dot product it with the vector x, y, z. And then over here, the n dot p, well, we get 0, and that, that's for everything in the plane. Any point in the plane would work for this, but certainly the 0 vector is in this plane, and so we could take p to be the 0 vector. And so what's u perp? So this is U. Remember, this plane is U. So then what's u perp? Well, u perp is the span of the normal vector of that plane. Okay, and later we'll do the Riesz. Oh wait, we already did this Riesz representation theorem that basically any linear functional on your space is just the dot product with some normal vector. Okay, and here we have an example of that. This set U is the dot product with this normal vector 1, minus 1, minus 1. Okay. Okay, but u perp in this case was actually the span of the normal vector itself, which corresponds to the fact that the normal vector, you can scale the normal vector by any amount, and it's still normal to the plane. Again, these are just examples. I'm not actually proving these or discussing them in more detail. So let's look at this next example. This one is just what happens when you pick the point for n dot p to be slightly off the origin, and you just take that plane and you just shift it off the origin. Now, this set of points here, this set U, is not a subspace. Okay, it's not a subspace at all because it doesn't even have the 0 vector. If you plug in 0, 0, 0, you don't get 1. So it doesn't have the 0 vector, but we can compute its orthogonal complement, and its orthogonal complement is nothing. Well, just the 0 vector. So in this case, u perp would just be the 0 vector in R3. In other words, the vector 0, 0, 0. Okay, last example, if u is the span of the first 3 vectors in an orthonormal basis of our space that has 5 vectors, so u is the span of the first 3, then U perp is going to be the span of the last two. Okay. All right, let's maybe just do, you should really know this proof, and it's in the book, and you should do it. So let's not do all of these. Let's just do this one, perhaps. So G and H here are subsets of our vector space. And we need to prove that this is true. So there's only one way to start this proof. Let X be an H perp. Okay. Need show that X is in G perp. Okay, what does that mean to show something's in G perp? Need show that for all y in G, xy equals 0. Okay, so let y be in G, and let's think about x dot y. Okay, well, what we've assumed is that G is actually contained in H. Okay, but x was in H perp. Let y in G. Then y is in H too, since G is contained in H as a subset. But x was in H perp by assumption, thus xy equals 0. And we're done with our proof because that's what we had to show. We had to show that this was true for all y, and we let y be in G, and it was arbitrary. Okay. This is an interesting one right here. Prove that for finite dimensional V, if U is a subspace, then V equals U. In fact, this is true, but I don't even need to assume that V is finite dimensional. If U is a finite dimensional subspace, then this is still true. Okay. Now this will fail if U is not a finite dimensional subspace. It could be true, but it might not be true. And exercise 16a gives you an example, which is basically talking about the Dirac delta function, which is not a function. But anyway, okay, so how do we prove this? So we want to prove that this is true, okay? And we're going to assume that the dimension of U is finite, even though V might be infinite dimensional, and in that case U perp will be infinite dimensional, but let's look in the case dim U is finite. So if the dimension of U is finite, then I can let E1 through EM be an orthonormal basis of the subspace U. Okay, nobody can stop me. So then let V be in V. Then what I need to do is write V as a sum of two vectors. I need to show that V is equal to a little u plus a little w, where little u is in U and little w is in U perp. Okay, so what I'm going to do is define little u to just be the orthogonal projection of V onto U, which has an orthonormal basis, and so we know this formula. In an orthonormal basis, the coefficients are just these numbers. And so this is definitely in U. So little u is definitely in U. That's good so far, because it's a linear combination of the basis of U. So it's definitely in U. All these are in U. Okay, and then define W to be V minus U. Okay. In other words, V is going to be this U plus V minus this U. Okay, so it's definitely kind of silly, but it's going to work. Now, how do we do it? We need to show, so to complete we've definitely got U and U. We need to show that this so defined W is in U perp. So need show W is in U perp. And actually, so, technically I need to show that for every x in U, Wx is 0. Okay? But first what I'm going to do is consider Ej, one of these orthonormal basis vectors in U. And I'm going to first show that Wej is 0. Okay, so what's W? W is V minus U, right? So I'm going to do V minus U dot with ej, well, that is v with ej minus u with ej. And what's u dotted with ej? So u is the sum of all these. Remember okay, this is, I called these, let's call this k. This index will be k now. ej is just one of the e1, e2, e3. And when we dot product it against all these, we're going to get zeros everywhere except for the term where k is equal to j. And in that case, we'll get ej dot ej, which is 1, and then a vej coefficient times 1. So in other words, we're going to get our vej from here, minus, and then a bunch of zeros, except one term with this coefficient, and an ej, which is 1, which leaves this subtraction, which is 0. So now we've shown that if ej is in u, which it is, then the dot product with w is 0. But now every x in u can be written as some cj, ej. And then when we dot product with w with that x in u will be w with a sum of the cj's, ej's, where cj's are some coefficients. And then this can be taken out, the sum over j can be taken out. We get, and the coefficients can be taken out. And we get w on the ej's, but all of these are 0. That's what we just showed. And so now we've shown that this is 0. Okay. And that accomplishes our direct sum decomposition. Well, it accomplishes that v is equal to u plus u perp. And then in a previous question, we showed that u intersect u perp is 0. Okay. And then that, by one of the results in chapter 3, that means that this is actually a direct sum. Okay. So now there's one more little piece here, which is this dimension formula. But that's just going to fall out of formulas we proved earlier. Remember, if you take the dimension of u plus w for subspaces u and w, that was the dim u plus the dim w minus the dimension of their intersection. But if we take w as u perp, we know that the dimension of their intersection is 0. So that and also we just showed that v is u plus u perp. So this part over here will be dim v. And then we've got dim u plus dim u perp. And that's exactly the right formula, except that we subtracted dim u from both sides, which is fine, you can do that. Okay. So let's look at this one. Prove this. And again, we need actually that the dimension of u is finite. This will fail in infinite spaces. So infinite dimensional inner product spaces, this will fail sometimes. So how do we show that two sets are equal? So the way to show that two sets are equal is to first show that one subset is a subset of the other. And that's one proof. And then we have to show that the other is a subset of the first. So there's really two proofs going on here. U and, so what we have? We had U and U perp. Okay. So let's first check if this is true. So there's only one way to do this. Let x in U. Okay? And now we need to show that x is in U perp. Okay. So what does it mean to be in U perp? It means you're orthogonal to everything in U perp. So we need to show that xw equals 0 for all w in U perp. Okay. But so let w be in U perp. Okay. Now we need to show that it's to be 0. But if w is in U perp, then it's orthogonal by definition to everything in U. So we're done. You would have to write what I just said. Okay. Now let's try the other way, that U perp, is it a subset of U? Okay, let's try this. So this is the direction that is, I think, going to need finite dimensional subspace U. So let's take something in here. Let X be in U perp. We need to show that, and let's call it V because of what we did before. You'll see in a second. So V is a vector in our vector space for sure. So we can write V equals U plus W, where U is in U and W is in U perp. And this is from the fact that we had this direct sum, which we just proved. And this required that dim U is finite. So we could choose an orthonormal basis, a finite orthonormal basis. So that's why this result's going to depend on U being finite dimensional. I think this is how it goes. Let's see. So how do we show something's in U? The way we're going to show that, so remember, to show a subset, you have to pick something in here and show it's here. So I picked something in here, and now how I'm going to show it's in U is I'm going to write it like this and then show W is 0. So I need to show W is 0. Okay. Now, any vector in a whole vector space can be written as a sum because of this result from before. Okay. So how do I show W is 0? Well, what do I know about V? V is orthogonal to everything in U perp. Okay. Oh, so V is equal to U plus W, where W is in U perp. Right, that's what it means to have this direct sum decomposition. And we just need to show that W is 0, and we know W is in U perp. But that means that, by definition, V is orthogonal to everything in U perp, so V is orthogonal to W. Okay, so that's what we know. But V is that U plus W, and then we get UW plus WW. And now you can see how we're going to get WW is 0. If only this term is 0, can we show that first term is 0? If this first term is 0, then we have W dot W is 0, which means W is a 0 vector by one of our properties of inner product spaces. Called it, was it definiteness, maybe? Or positivity, I can't remember. So why is this 0? Well, let's look at what these things are. We know that little u is in U, and we know that little w is in U perp. Oh, then by definition, their dot product is 0. End of proof. This implies W is 0 by definiteness. I don't know if I spelled that right. Okay. Let's skip ahead to the orthogonal projection. So give a precise definition. So what is this thing? The orthogonal projection. Well, it's going to be a map that eats a vector in our space and spits out a vector in our subspace. And in order to define this, we're again going to need that the dimension of U is finite, because we're going to use the fact that our whole space is a direct sum like this. And this is true if the dimension of our subspace is finite. So V can be infinite dimensional, but our subspace U needs to be finite dimensional in order to define this projection, because we're going to use this. Okay, so to define this projection, we need to let little v be in big V, and then we need to tell you which vector it should go to. So define Pu of this little v to be equal to the little u in its some decomposition. I'm going to call it a decomposition because I'm sort of breaking it into two terms, because in its direct sum decomposition, little v equals little u plus little w, where little u is in U and little w is in U perp, coming from capital V is U direct sum U perp. Okay, so because we proved this result, we know that any vector in the space can be written as uniquely, the U in its unique direct sum decomposition. And so just, essentially just throw away the U perp term, and that's going to be the output of this map. So what does this map do? This map right here takes a vector in V and just spits out its component in the U subspace, throws away its component in the orthogonal direction. And so it just spits out the first term of that decomposition into two pieces. Okay. Good. So we'll do some of these in class. You should really know how to do them. They're very easy. There's a lot of them, so it looks intimidating, but they're very easy, each of them, I think. Maybe there's I think they're all very easy if you just think about the definition. I mean, let's try one. So let's try this one. We have to prove this, okay, that pu of x is equal to x if x was already in U. Well, remember, capital V has a direct sum decomposition into U plus U perp. And so, if x is in U already, there's a unique way to write it as a sum of two terms that has to be x plus 0, right? And then pu of x is by definition where you throw away this term and keep this term, which is x. So that ends the proof. And I hope you agree that that was a simple proof, provided you know the results that that we have in our possession already. Okay, so yeah, maybe I'll just comment on this. This is maybe in some ways the definition of what it means to be a projection, that if you do it twice, that's the same as doing it once. So this squaring is doing the projection twice. But again, what we just proved is that if you're already in the space, then doing the projection doesn't do anything, right? It just keeps you where you are. So if you do the projection once, you're already now in the space, and if you do it a second time, you didn't do anything new. Okay, so a lot of these are very connected. So it takes some time, really understand these. And yeah, we already even used this formula in the proof of something. I forget, maybe it was the proof of this. Maybe it was the proof of that. Yeah. Okay. So I think I'm going to leave the rest for the next video. Yeah. Is there anything else I should do here? No, that's pretty good. Okay. See you next time.